Hello again. I would like to express a warm welcome to everybody. Now I'm going to have my second lecture on doing phenomenology in science education. In my last lecture, I related to mechanics that is taught in grade 10 in Steiner-Waldorf schools. Today I'm going to relate to grade 11, being taught in Steiner-Waldorf schools with the focus on electricity. I would like to show how the concept of charge and the concept of field are entangled in that main lesson on electricity. I'm a physics teacher. I'm a professor for school pedagogy with the main focus on phenomenological teaching methods. And at the moment, I'm in Kassel in my lab in the Institute for Subject-Related Methodology. That institute is closely related to Alanus University of Arts and Social Sciences. In order to develop my presentation related to grade 11, I would like to show first what is the pre-knowledge of the students in grade 11 if physics is taught in the curriculum of a Steiner-Waldorf schools according to the proposals of Wilfried von Mackensen. He proposes to introduce voltage in grade 6, current in grade 7, and electromagnetism in grade 8. And if you start the main lesson block in grade 11 with electrostatics, I recommend to relate briefly to the pre-knowledge the students got in grade 6, where voltage should have been introduced. And you might do it with a couple of demonstrations or experiments, and I am showing them briefly. Therefore, I am just changing a little bit the zoom of my camera. And here I have a plastic foil. And this plastic foil here, I'm going to press firmly into place here on the table. So I have the synthetic material of the tabletop. I have that plastic foil here. And now I'm going to take it away, and I will be very quiet, and you might hear something. Okay, here I have it. Here I have a paper stripe. Oh, it's pretty clear. And you can also have here this one. And I'm not going to show it, but of course you can have a glowing lamp. And if it's dark, you can see the glowing here. Okay, that is one way to do it. Another way to do it is that you have a tube here. You rub it. That's clear too. And in case you have the glowing lamp here, you will find that if you have a spark over in that position, then you will never ever get one here. But this does not interfere with the spark over in this position that is still possible. But once you have got a spark over, then you will never ever have it in this position. In class, if it's dark, I'm just moving the glowing lamp like this. I will have a lot of spark overs, and on my way back, I will never ever have it. I would be able to add further experiments. I'm not going to do it, but I'm going to sum it up a little bit on the Blackboard. And what I actually did, I'm going to denote with the term to electrify. I could use to charge as well. If I use to electrify, I have the freedom to introduce the concept of charge appropriately later. So I recommend just to use this term here, but it doesn't matter, of course, if the students just use to charge because it's widely spread in the language. To electrify means that you have two different materials. They are synthetic materials. And first of all, you have contact, and you have separation. And then you have a potential for appearances. And those appearances can be the glowing of the glowing lamp, it can be the crackling, it can be the moving of the paper stripe, and those appearances that happen in that context we call electric appearances or electrical appearances. You have the potential for electric appearances, and this potential for electrical appearances is denoted in physics as voltage. So in grade 6, students learn you can produce voltage if you have two different synthetic materials, you bring them into contact, you separate them, and then you have the potential for electric appearances. And as soon as the electric appearances occur, then this potential is gone. And you can especially show that using the glowing lamp. So I'm just changing the color here to derive the physical quantity voltage from this procedure. Okay, that is something like a procedure and is the condition that voltage occurs. And you really have to acquire knowledge which two materials, different materials, have the best effect. Okay, that is one part in grade 6. And the other part is that you have two classes of materials. And the synthetic materials we used here have the feature or have the electric characteristics that if something is electrified, it is like small islands. You have a tube, you have the glowing lamp. If the glowing lamp glows, then that part is gone, but the other part is still present. You have one electric island beside the other. And in Latin, island means isola, And from that, in German is derived Isolatoren, and in English, insulators. That is one thing. And if you have other materials like metals, you observe something else. I'm going to show that. Here I have metal. Here I have synthetic materials. And that synthetic material is an electric insulator that is like the plastic tube. But now I'm going to electrify this tube. And by rubbing it, that means, of course, bringing into contact and separate, bringing into contact and separate. So rubbing is exactly the same like bringing into contact and followed by a separation. And now I can just bring it into contact here, and something happened. I can bring it into contact here. I can bring it into contact here. And the electrification seems to increase. And what is really interesting is that it doesn't matter at all where I actually bring the tube into contact with the insulated metal plate. And now, of course, I can start playing. I can make all the things I would like to do. And now it doesn't matter where I'm going to touch it. I'm going to do it here. And then it's gone. The potential for electric appearances has collapsed. Okay. I take this away. And this class of materials that are predominantly metals are called conductors, and in Latin, conducere means to bring together. And the electrification is brought together on the whole metal plate. And from this conducere, to bring together the electrification, is derived conductor. Conductors can be electrified as a whole. And if the electrification collapses, it's completely gone. Insulators have the electrification located on insulas. And if you have these islands here, then it doesn't matter what happens in one island at the position of another island. Okay, so to get started in grade 11, I would recommend just to remind the students that the concept of voltage had been introduced in grade 6 as a physical quantity to characterize a state of electrification. You get the appearances if the state of electrification collapses. As long as it hasn't collapsed, you can get very different appearances. So the potential is a real potential for very different appearances. And then you have two classes of materials, electric islands and materials bringing together the whole electrification over the whole plate. Okay. If you have dealt with that, you can use the electrostatic machine or the electrification apparatus I'm going to present now. And that is something like bringing together everything what the students have learned in grade 6 related to electricity. And that can be the point of departure in grade 11 to start with electrostatics again. Now I'm going to take this electrification apparatus or electrostatic machine. It's here. And here you have a cotton fabric that is pressed firmly into place with a plate here. And if you start turning it here or rotating it here, then you have bringing into contact and separation. And then you have an insulated metal plate here that can be electrified. I'm going to fix the paper stripes here. And now if I'm going to rotate here, it's pretty strong. And now you can start playing. This is an experience of having power. And you can show your courage by just moving here and everything will be gone. And you can show the students that it doesn't matter where you actually touch it. Oh, it's nice. So I had several spark overs here, and I think you could hear it. I will do it again. Okay. So far, relating to grade 6. And now I'm going to change my place. I'm going to my computer and I give you some hints where you can buy it and where you have the link to our YouTube channel where you get all the safety advice using this machine. We will see in a minute. Okay, now I would like to share my screen. Here you have our website of our seminar, and we are cooperating with the Pedagogical Research Center within the Federation of Steiner Waldorf Schools, and we are developing a lot of teaching aid materials. You can buy them in the Lehrmittel shop. You have to go here, change the language into English. And if you just put in here electrostatic machine, then you get the electrostatic machine. It's a bestseller in our department, and you will find here the link to our YouTube channel, and there you will find with English subtitles the safety advices and further details. Here you have the glowing lamp. Here we have an adapter for the glowing lamp that can be connected here with 4mm plugs of cables, and you have the blades here as well. And if you just use this adapter for the glowing lamp and connect it with a grounded cable with a 4mm plug, you will never ever actually get an experience of that spark over, and it will not hurt at all. Okay, that is one thing. The other thing is, in my booklet, Physics in Waldorf Schools, I have a whole chapter dealing with electricity, and you will find further experiments and further comments there. You can buy it at waldorfbuch.de, and here you can change also the language, and if you have the English language here, you will find it immediately. So far related to the websites that might provide these materials. And now I'm going to continue in front of the Blackboard relating to grade 11. We will meet in a minute. After having reminded the students about the topics of grade 6, and that will need approximately half an hour, I would recommend to start with a demonstration. And for example, you can use the electrification apparatus here. You can just electrify it. And you can explore the space around the conductor plate, and you will see that the paper stripe is always perpendicular. I just use the big one in order to have a good projection. In glass, usually I use this one here. And then you can just go here, and you can also explore what's going on here at this position, just to show you the way I'm proceeding in class. And here we got it, and that can be much stronger. Like this. Okay. And if you have got this experience, you can use a sphere conductor here. You can investigate or explore the space in between using this paper stripe here. And I'm not going to do this. And after you have done this on the first day, you can proceed on the second day in a way I'm going to show now. You start to electrify this here. Then you take a contact metal sphere here with an insulated handle. It still works, but maybe we help a little bit. Oh, something happens. Wonderful. And now, mind the noise. First you hear the spark over, then you hear it touching. You could hear the spark over first, then I touched it. Okay, and now I can touch it here, but it just doesn't have a lot of influence here, and now it's gone. I'm going to take away everything. And now I would like to review a little bit the experiments or demonstrations I did. And what I have here is the blade of the electrification apparatus. It's connected here with the huge tube you actually have here. And this huge tube here was brought into contact with the cotton fabric here, pressed firmly into place with this blade here. And this blade here was connected with the ground here. And I'm going to sketch the ground here. And I'm going to use here just the mounting of the huge tube here at this position. And now I'm not drawing it exactly, but you have something like the walls of your room here and the walls of your room here are connected with the ground. And if I look at this area here, I actually could realize that in this area here, we had an effect of electrification because the paper stripe got an orientation. And you can get this state of excitation in the surrounding of the plate, even if there's no material substrate. You can have it in the vacuum as well. And if you just look at it very carefully, I'm just adding here the mounting of the plate as well. If you look at this carefully, you can see that you have always an orientation perpendicular to the plate. And if you have the small paper stripe, you can see that it moves a little bit, it trembles a little bit here, the trembling is stronger here and here as well. And now you can describe that state of excitation. And I'm not going to derive that completely. You will find it in literature and you realize, okay, it really depends on the distance you have. You can introduce the poles using the glowing lamp. And that is the minus pole here, and the Earth is the plus pole here. And you will see if you have a short distance, then you have a strong excitation here. So you have to draw a lot of lines here. I have to draw a lot of lines here too. And I don't know if I should draw one or not. You have to decide, and you get the lines get an orientation by definition from plus to minus. So I have to draw it this way. And you have the electric field here. And you can characterize with these field lines here a state of excitation where the electrification is also present in the space between the poles. That will be new at the very beginning of grade 11. And now I'm just going to take this plate here and I just draw it with the green color. And I draw it here once again. And here it is mounted. Here I have the ground, and I have another plate here. It's mounted too. And now I'm not going to draw everything. I'm just going to draw the sphere of the conductor with the insulated handle here. And if I have an electrification at this point here, then I will have an electric field here that looks this way. Oh, no, I have to draw it like this. And if I'm going to move that conductor sphere here at this position, I will have the electric field here, and it will just follow the movement. So you have a displacement of the field. And if the conductor finally arrives here at this position, then this plate will be electrified and you will have at least some part of the field being attached to this conductor. That is 1, 2, 3. If the field is completely displaced, I should draw 4 lines, otherwise 3 lines. And now you can just develop with the students that if you have an electrification, what is new is that you have a state of excitation here. And this state of excitation can be described geometrically using the electric field. If you go at this position here and you start moving conductors, you can displace the field while the field is attached to the conductor. So what you are actually doing here is that you move electric fields here and you attach it once again on another conductor. And then you can introduce with the students that the attachment of the field in electrostatics is called charge. And the structure in the space in between is called electric field. And by reaching that position, you can realize, okay, the space in between is characterized by a geometric structure. The attachment to the conductors is characterized by charges. And the displacement of the field corresponds to a transport of charges. A collapsing electric field means that the same amount of positive and negative charges are neutralized. A strong field means highly charged. And so you can sum it up by comparing the field approach and the charge approach. And I would like to sum it up now. And I will clean the Blackboard in order to do so. We will have something like a comparison between 2 approaches, and people having studied physics know that the divergence of the electric field is proportional to the charge density. And so this Maxwell equation characterizes that how field and charges correspond. And usually people read that equation in the way that the charges are the origin of the electric field. I didn't do that. I just introduced the term to electrify, and then we can see the correspondence of it. And the field aspect actually characterizes the space between the conductors, while the charge approach indicates the attachment of the field to the conductors. And now I'm going just to write a table, and we can see that we do not have to interpret this comparison in the way that the charges are the origin. These are simply 2 aspects to characterize an electric state of excitation. So I have the field here. And I have the charge here. And the field characterizes the space between the conductors, while the charges indicate the attachment of the field to the conductors. And if you have got this correspondence, then a strong field means highly charged. The displacement of the field means at the same time the transference of charge and the collapse of the field means at the same time a neutralization of positive and negative charges, and the tendency of the field to collapse corresponds to the fact that opposite poles attract. That is also corresponding. I'm just going to denote this. You have a tendency to collapse. And you have here opposite poles attract. I'm just going away once again that you can have a screenshot now. Okay. And I wanted to introduce today that you have in a phenomenological approach the correspondence of charge and field, and you can introduce it without giving this correspondence a causal structure. It's the same idea as in grade 10, that forces as an abstract concept and vectors aren't the perpetrators. They are an abstract description of an interaction. And you can see here in the correspondence that the charge approach relates to the attachment to the material, while the field approach relates to the state of excitation in the space between the poles. So far related to doing phenomenology in grade 11 in a Steiner Waldorf school with the main focus electricity. and I am looking forward to having my third lecture relating to grade 12. See you. I hope I will see you again. Bye-bye.